Okay, good evening. Hi. I'm going to go ahead and give my typical caveat of being a frogman this evening. The change in season has made me sound about an octave lower than normal. And if I get all choked up, I apologize. It's not because I'm emotional at seeing everybody here. It's just the get a little bit of fall laryngitis. Let me give you a little bit of background about myself. My name's Les Johnson. I do work for NASA at the Marshall Space Flight Center down in Huntsville. But I'm not here representing NASA this weekend, and this will be the only set of slides that have the NASA meatball on it, because I want to give you a little bit of background into why I'm here to talk to you about something as far out as interstellar travel. And it has been my passion since I was a kid. I, of course, read all the science fiction I could read. I still do. I'm a big science fiction fan. I dreamed of going to the stars. I'm actually the co-chair of a workshop that's going to happen a week after next in Oak Ridge called the Tennessee Valley Interstellar Workshop. I'll be glad to answer questions about that after the panel tonight or the presentation. It'll be about 45 minutes of questions and answers. If you have questions during the program, that's fine, although I'd rather wait till close to the end. We can do them as we go. By way of background, I did do my graduate work here in Nashville at Vanderbilt several years ago. Ended up living in Huntsville, where I've been for, a quarter of a century now. I've been at NASA for 25 years. And in the course of being there, I have kind of a reputation. One of my colleagues is getting a little bit on the fringe. I'm sure none of you all can relate to that, right? No! NASA is kind of a corporate kind of company, kind of government agency, and I'm the guy who's thinking about what we do not just next, but what we do next, after next, after next, after next, and how do we lay the groundwork for that future. And the talks I'm giving here this weekend are a part of that story. Tonight's the far-term vision. Tomorrow I'll be talking about a little bit nearer term. But as I go through the presentation, you'll see why my talk tomorrow about solar sails is directly relevant to the topic at hand this evening. By way of background, I'm also a science fiction writer, and I have some of my popular science as well as science fiction books in the back. A couple of years ago, for Bain Books, I edited an anthology called Going Interstellar, and it was in here the original stories by several science fiction writers about what a realistic interstellar voyage might be like. There's no warp drive. I'm sorry, there are no wormholes. It's all stuff that what we understand about the way nature works today, how might we go to the stars? And within this, I wrote some essays that are the science behind the fiction of the stories. And my publisher liked it and commissioned, I hope this doesn't turn any of you off, but she thought it was such a good idea that she commissioned a professor at UT Austin to do a teacher's guide to go along with the book, which they give away for free at the publisher's website. And then she sent copies to high schools, which I thought was way cool. Trying to get kids addicted early to science, and maybe a little bit to literature, right? Because I think that we need a more well-rounded population, frankly. And so anyway, that's kind of my passion. I'm writing science fiction, writing popular science. I've been writing and talking about how we might really go to the stars. Well, about a year and a half ago, almost 2 years, National Geographic contacted me. They were doing their 125th anniversary issue, January 2013, and they wanted it to be dedicated to the future of exploration. And they were doing a series of articles about Antarctic exploration, exploration of the bottom of the ocean, people going into the Andes, people, going into the jungles doing exploration. And they wanted to talk about that ultimate trip of exploration, going to the stars. So I was interviewed and I answered a lot of questions. Next thing I know, they're sending the proofs of the article for me to read and make sure it's all right. And they're very meticulous at National Geographic. Well, shortly after that, they called and they said, "Hey, Les, we've got pictures of all these explorers. We'd like to have a picture of you in our magazine." So I was actually photographed in the January 2013 issue of National Geographic. This is me holding what's called a solar sail, piece of the solar sail. In my opinion, out of all the ways I'll talk about tonight about how we might go to the stars, this is the way I think it's most likely to happen in the nearest term, which is using lasers and this lightweight material called the solar sail. Now, I have to admit, I was very flattered to be in National Geographic. My sister, of course, couldn't believe it, right? Family can't believe stuff like that. But I felt really guilty because when I got the issue, I'm reading stories about people who've had their toes frozen off in Antarctica, who worried about getting malaria. And the worst I had to worry about during the day was getting a sunburn as I stood out under the blue sky. So it was a real hoot. I'm from East Kentucky, that's where we talk. And it was a lot of fun. But that's part of why I'm here. Part of it is I'm also an unrepentant science fiction fan. I was inspired by science fiction. You may recognize some of these spacecraft. I'm absolutely a fan of irreverent science fiction as well as serious science fiction. And I'm still disappointed that there hasn't been a sequel to Buckaroo Banzai. Also inspired by science fact. I am a child of the 60s. I was born in 1962. I was 7 years old when Neil Armstrong walked on the moon. I thought we'd have a Mars base by now. Okay? I'm sorely disappointed. I understand why we don't. That's a topic I'll be glad to talk about later on this evening if you catch me in the hall and offer me a beer. But it's just really hard. And as you saw the news this week, we've had 2 big setbacks in private commercial space this week. It's really hard. But it's not so hard that we can't do it, and I think we need to dream big. Did you know that before 1992, we did not know that there were planets around other stars? The only people who knew that were science fiction fans, right? And they didn't know it, they just believed it to be true. But there was no empirical evidence to say that there were any planets anywhere else in the universe except those that orbit our sun, okay? Well, in 1992, there was this little thing called a pulsar, very energetic, bright object in the sky that are very regular. They give off radiation, they rapidly rotate, they give off radiation very regularly, and people want to use them for navigation. I mean, they're so regular, they're like a clock, and you can use it for navigating. They all have characteristic signatures of the radiation and how rapidly they spin. But there was one pulsar that had an irregularity in its emissions. And so astronomers looked at it and they figured out the only thing that could possibly be causing that was a very massive planet, bigger than Jupiter, close to the pulsar. So that was the first empirical, though indirect, evidence of a planet around another star. 1992. Since then, there's been an explosion of the discovery of exoplanets. Lots of different ways that have been discovered, and I'll talk a little bit about that. But there are stars out there that are like our sun, and we're finding stars like our sun with planets, as well as lots of stars that are not like our sun that have planets. But this is way cool. 51 Pegasi. It is not a pleasant place to be. We expect it has a temperature about 1,200 degrees centigrade, pretty hot. But it could have other planets that we just don't know about orbiting that star. This number should actually be higher, but this is the number of confirmed exoplanets. For a planet around another star to be considered confirmed, it has to be detected by 2 different methods. You can't just have one way of detecting it and say it's there for sure. There has to be a totally different method, totally independent team using a different physics to confirm that it exists. And we believe that there are now billions, if not hundreds of billions of planets out there, based mainly on a mission called Kepler. Now, Kepler was looking at a region of our galaxy. You see that little region right here? We're in there somewhere. And it was looking at this region of the galaxy, and it was staring for years at a star field. And it was looking for a regular dimming or shadow around these stars. The way I like to describe that is stars are so big and so bright, and planets are so small and so dim, that imagine going out there tonight, standing in front of your car, turning on the high beams, and seeing a mosquito fly in front of the light. You wouldn't be able to see it was there. And until the last 20 years, we didn't have detectors sensitive enough to notice the shadow of a mosquito in your headlights, which is the equivalent of what we're looking at here around these stars. But the Kepler stared for years at this region of space and found 3,000 to 4,000 exoplanets. Now, planet hunters on the ground are using different techniques to go look for these exoplanets and confirm they exist, and that number keeps rising. So we think there are hundreds of billions of exoplanets in our galaxy alone. Yes, sir, Mike, yeah.
What are the different techniques?
Greatly dim. I get this talk a lot. I know how to set people up sometimes. There's the Doppler shift. You're familiar with the Doppler shift probably. It's you stand there at train tracks, the pitch of the train changes as it comes toward you and moves away. It's because the wavelength is either being compressed as it's moving toward you, or it's expanding as it's moving away from you due to its motion. Well, it turns out that our Earth, as small as it is, put this in perspective, 108 Earths could fit across the equator of the sun. okay? So this little teeny tiny Earth, 93 million miles away from this really massive star, we're held in our orbit around the star by the sun's gravity. Don't forget, the Earth pulls on the star also, okay? And what that means is, as we orbit the star every 365 days, we're slightly tugging on our star. That causes a slight wobble in the star and changes its light emission, just like a train causing a Doppler shift. If you're looking at the star from over here and the Earth is here, the sun is pulled ever so slightly toward the Earth, and that changes the frequency of light, the wavelength of light, coming from the sun. We have stars sensitive enough, instruments sensitive enough, to detect the Doppler shift caused by planets orbiting other stars. Okay? It's the Doppler method. It's another way to confirm. So if they look and they see this wobble, and it's a regular wobble, and they figure out what the orbital period is, and it matches what the Kepler said it saw from the light dimming, it's an independent confirmation that there's a planet around that star. The transit method I've already described, that's the mosquito and the headlights. There are other methods, gravitational microlensing, astrometry, you name it. I'm not an expert in exoplanet detection. You can go look up how these are done. These are less used. The two most common are the Doppler shift and the transit method. There's a catalog out there now of potentially habitable exoplanets. It's based on whether or not the planets are in the so-called Goldilocks zone, not too hot so that water boils away and there's no water on the planet, not so cold that it's permanently frozen, but just right, kind of like where the Earth is, where you have a warm climate, liquid water, good solute. If you have chemistry, you know that water's a great solvent. Do all kinds of interesting organic chemistry in water. You want to look for that. You want to look for planets that aren't too big, aren't too small, and a star that's not a variable star that periodically gets really bright and fries the planet and it gets really cold. All those things rolled together go into this habitability index. And so they're looking at all these exoplanets, not really looking at the planets, but inferring what the conditions might be like. We can't actually see any of these planets yet, but there is a way we can. And I'm hoping that before I'm dead, someone will at least plan or launch the mission that will let us look at these planets, and I'll describe what that is. There's also a planet around the nearest star system. The Alpha Centauri system is close by. Turns out there's at least one planet orbiting one of the 3 stars in that system. Begs the question, so what? How do we get there? Well, let's talk about distance. Let's talk about how hard it is to get there. In our solar system, thanks to a native of Huntsville named Mike Brown, who's at Caltech, Pluto is no longer considered a planet. So when I talk about the distances to the planets, I'm going to talk about the Earth, and I'm going to talk about the most distant planet, which is Neptune. So the Earth, teeny tiny Earth, is about 93 million miles from the sun. I don't know about you, I can't imagine what 93 million miles is. I mean, that's just a big number. Big number. But let's shrink that down, as astronomers do, and let's call that distance 1 AU, 1 astronomical unit. We've defined a new term, okay? So 93 million miles is equal to 1 AU. I'm going to further define it for the purposes of this illustration in this room and say that 1 AU is now 12 inches. My foot's 1 foot long, okay? So the sun is here. The Earth is a foot away, okay? On this scale, Neptune is 30 feet away. So it's about a little bit beyond you, so right there, okay, in this room, about 30 feet that direction. That's the outermost planet. Pluto is at 38 feet. If you're old school and you still consider it to be a planet. It takes us about 11 years to send a spacecraft to Pluto. About 11 years.
Voyager took how long to get outside? They're still arguing whether it's outside the solar system.
Voyager's at 130 astronomical units. Now I've got a slide on Voyager here in just a minute. At this distance, where 1 foot is 93 million miles, the closest star is 51 miles away.
Ouch.
Okay? Let that sink in. 1 foot, 5,280 feet, times 51 miles, times 93 million miles. is how far away the nearest star is. This is an unbelievable challenge. I mean, we are isolated, folks. We are absolutely isolated. It's a very great distance. Yes, sir.
I know it's not a big deal, but since we're actually measuring things in this talk, our star to star distance to the nearest star, how much would that vary, if you can tell me off the top of your head, like in 1,000 years or something?
Not a whole lot in 1,000 years, but the Earth is moving around the center of the galaxy. The star, our star, is with the Earth with it. And we go around every, 100 million years? Something like that. Some unbelievably large number. In fact, when you start thinking about deep time, it's almost as unimaginable as deep space, right? But we are moving. And what's really cool is some people think that some of our comets are actually comets that formed around other stars, and our Oort clouds have kind of bumped up against other stars' Oort clouds over time. And so there are actually serious scientific thoughts that maybe some of these comets that plunge in every now and then have been disturbed by the passage of other stars and their planetary systems, and they may not have originated around our star. So that's pretty cool. It's also a great fodder for some stories I might write. So you never know what you're going to find out there. Voyager. Voyager is traveling pretty fast. It's traveling at almost 1 million miles a day. 900 and some thousand miles a day. It's been flying since 1977. And out of that 270,000 astronomical units to the next star, it's got 130. At that rate, it'll be over 70,000 years before Voyager reaches another star. Clearly, it's not the way to go. Chemical rockets are not going to get us there. So, what can? I'll tell you, there is some discussion now of an interstellar probe, a project to send not a probe to another star, but as a follow-up to Voyager, to go further and faster than we've ever gone before. And there are various technologies being considered to do that, where we might be able to send a probe to 250 astronomical units, roughly twice the distance that Voyager's traveled. But the goal is to send that within 20 years of launch. Now, why 20 years? Why not 25 years? Why not 30 years? Well, 20 years we think we might be able to do with some advanced propulsion technology. And the other is purely selfish on the part of the science team. By the time you get to be a PhD researcher of the clout to be able to propose and lead an interstellar probe mission, you're going to be in your mid-career. Probably have published, probably be at a university or research institution. You're probably going to be in your 50s. If you build this thing, it's going to take 5 to 10 years to build it. You're 60. By the time the data comes back, they want to be alive to see the data. That's the 20 years. I'm not kidding. They don't want to be dead when the data comes back. So the challenge that's been laid out for us, the propulsion team, is to do this such that you can get it there in about 20 years. I saw a question, but you might want to go to a mic or wait. Go ahead. I can get you.
So it might be like a conversation for later, but how do we get data back from something like that or even Voyager?
It's really hard. Voyager has on board a plutonium power pack called a radioisotope fermionic generator, an RTG. Basically, it's a little ball of plutonium. Plutonium is highly radioactive, not something you want in the room with you. And it's radioactive, so it gives off radioactive particles, and that is translated into heat. Okay, so it keeps the spacecraft warm. And there's also a power source. You can take that heat to generate electricity. So we know how long it takes for the amount of plutonium that's on board Voyager to decay, because we know its half-life. And based on that, Voyager will last another 10 years. And then it won't give off enough radiation to generate the electricity to power the transmitter to send the data back home. Okay? But both Voyagers are still calling home about every week. Okay? And we have to use the Deep Space Network, those big antennas, to find it and know exactly where to point it to hear it.
So can it transmit things other than just where it is, or like?
Very little. Its data rate and the ability to transmit data has dropped The cameras have long since been turned off because there's nothing to see. But the particle and fields measurements, it's counting ions, neutral atoms, things like that, to study the density of the vacuum. Because no vacuum is absolutely perfect. Interstellar vacuum is something like a hydrogen atom per cubic meter. And that's as close as you can get to vacuum in my book, right? But it's not complete, so you still have counts. And when you're flying through it, you know, 1 million miles a day, you're going to count a few hydrogen atoms. So they're doing science, but not as much science as Voyager did in the inner solar system. So how do you do this? Well, there are different propulsion technologies. If you look at my shirt, it says in-space propulsion. I used to manage NASA's in-space propulsion technology project, and I worked on a lot of these. But I'll tell you about what these are. Electric propulsion is pretty cool. Let me explain real quick about rockets. Okay, imagine I'm up here on a skateboard or roller skate, all right? And I throw a bowling ball this way. What's going to happen to me? I'm going to move the other way. That's a rocket. Hot gas goes this way, rocket goes this way. Now you're rocket scientists, okay? That's it. Boom! That's it. All right? So the key is get your exhaust moving as fast as you can so that momentum is conserved. Momentum is conserved. That's lesson 2, right? Physics, conservation of momentum. You do something, every action has a reaction. Throw the hot fuel that way, you go this way. Throw it faster, you go faster. All right? So electric propulsion, instead of chemical combustion, uses electric fields and ions, protons, or electrons added to or stripped from some heavy atom that are accelerated across, I get excited, accelerated across that electric field and thrown out the back of the rocket to make it move. Well, the neat thing about electric propulsion is it's very low thrust, so it'll never get you off the planet. But once you get into space, you can get about 10 times the total push per pound of fuel with an electric propulsion system that you can with a rocket. So in rocket, I'm giving my tutorial of how to be a rocket scientist tonight. Impress all your friends, right? You guys impress the heck out of me with what you're talking about. So I'm also not turning on my Wi-Fi. I know that. I've learned something. Don't turn it on. The figure of merit is called a specific impulse. It's a measure of efficiency of a rocket. The units are seconds, all right? So chemical rockets have a specific impulse of about 400 to 600 seconds. Electric propulsion systems are about 7 to 10,000 seconds. So you get a lot more change in velocity per pound of fuel. It's a little slow, it's a low thrust, but you got time. You got 20 years, right? So it's a pretty efficient way to do it. We looked at a design that would do this. Solar electric won't work to get your electricity from the sun because you're moving too far from the sun. Plutonium doesn't put out enough heat to generate the power you need to drive it. So we figured out you'd have to take one of the nuclear power plants around here and miniaturize it and put it on board. Now that's hard. The Russians have 30 of these. You don't want to hear this. If you get nervous about things, plug your ears. There are 30 dead nuclear reactors orbiting the Earth. Okay? And if you heard my talk this afternoon about orbital debris and things come crashing down, okay, you don't want to think about that. But they are up there. They're highly radioactive. They use uranium. They're sitting up there glowing. They're dead. But you can use these things safely going out into space to power your ship. The problem is it's expensive. We did a cost estimate. It would be on the order of several billions of dollars to take a nuclear power plant, miniaturize it, build the electric propulsion system, put it on the craft. Then it would take several big rockets to launch it, assemble it, and make it go. It doesn't look too practical. Electric propulsion is real. It's flying. If you go look up the Dawn mission, DAWN, it couldn't happen except with electric propulsion. It's visiting 2 main belt asteroids. Ceres and Vesta. It's a great system. Solar electric propulsion, not nuclear, but it just isn't going to work for nuclear, for going to the stars or the interstellar probe. This is how big it would be. And what you see, those big panels are not solar panels. Those are radiators to get rid of the waste heat from the reactor. Okay? Really big, really hard to do. Chemical rockets can't do it. And the only other thing that might be able to do it is a technology I'm pretty passionate about called a solar sail. Now let me explain how a solar sail works. You can't feel it, but when light reflects from you, it's pushing on you. Light has no rest mass, but it does have momentum. Remember, the key to making a rocket move is momentum transfer, right? But a solar sail is not a rocket. So what happens is the sun is always shining in space, okay? Always got the sun, unless if you're in shadow of the Earth, and that just very short if you're in Earth orbit. But the sun's always out. And as that light reflects from a large, lightweight material, a sail, it will push on it. It's a small push. It's about an ounce of force per football field of area. Very small. But it's constant. It's always pushing on you. Okay? So if you can unfurl a football stadium sized or larger, thin film material into space, it can propel your spacecraft pretty fast. Now you have another thing working for you. It's called the inverse square law. Not too much math, okay? Basically what it says is, if this is the sun and this is the Earth, there's a certain amount of light falling on my sail. If I'm moving away from the sun and I double the distance, it's not half the light. It drops even worse than that. It's only 1/4 the light. So that's 1/4 the push. Not very much fun. But if you cut the distance in half, you don't get twice the push. You get 4 times the push. And if you deploy it in Mercury, you get 16 times the thrust than you do if you deploy at Earth. So the plan is to take a sail that's about 200 meters on a side, that's pretty big, deploy it close to the sun, and it will get the acceleration needed to take a probe about half the size of Voyager. We've got a lot better electronics today than we did in the 70s, a lot better materials, we cut the size down. And it can go fast enough to get to 250 astronomical units within about 20 years of launch. So we can do this, okay? Have we flown a sail that big? No, we haven't. But we're working on it. NASA, the Europeans, and the Japanese have been developing solar sails, and these are going to be flying real soon. We worked on one at NASA where it was a sail we tested in the world's largest vacuum chamber. Believe it or not, that's located in Sandusky, Ohio, about a half a mile from the amusement park that's up there. 20 meters on a side, translated into units you and I can relate to, that's 100 feet across. That's how big that sail is. We then flew a small sail in Earth orbit from what's called a 3U CubeSat, which is a spacecraft about the size of a loaf of bread. It was 10 square meters in area. There are 2 missions that I'll talk about tomorrow. Near-Earth Asteroid Scout, for which I'm the principal investigator in my day job, which will fly an 85 square meter solar sail going to an asteroid, and Lunar Flashlight. The Europeans are working on a sail, and the Japanese beat us all to it. In 2010, they launched Icarus, interplanetary kitecraft accelerated by radiation of the sun. Now, if you know your Greek mythology, you'll think they're crazy for calling their solar sail Icarus. I have to admit, it was lost on me why they did that. But it worked beautifully. This sail is 14 meters on a side. It's been flying in deep space for 3 years. Okay? 100% successful. They demonstrated that they work, that they can navigate with sails, and they know what they're doing. They have a mission plan to Jupiter that will launch within the next 5 years. If you really want to go that 270,000 AU, you got to think big, however, really big. Think a sail the size of Texas. Okay? The one thing I want to get across to you tonight for traveling these distances of 270,000 astronomical units, all those miles to the nearest star, you can't think small. You got to think big, all right? Bigger than anything we can do today. I'm not saying we know how to do this. What I am going to tell you as a physicist is that the laws of physics will allow us to do this. Now, if you're an engineer, you're going to think I'm crazy because you don't know how to build it. But I'm telling you it's not impossible. And when you tell somebody it's not impossible, they're going to be creative people to work out how to do it. So we have a roadmap. I've taken sails from where we are today, which is down here, all the way to the sails that are down at this end of the scale. A very large solar sail deployed well inside the orbit of Mercury. Think of 6 to 10 solar radii really close to the sun. Can get really, really large accelerations and can go to the stars maybe in a century or less. If you want to speed it up, think about putting a big laser in space. so that that pesky inverse square law doesn't kill you as you're moving out of the solar system, and you can continue pushing on the sail as it leaves. The idea here is to put very large laser, think something that has the energy output of all of humanity today, okay? I'm dreaming here, it's okay.
You said think large.
Think big, don't think small. And you can use that laser to stay focused on that sail and send it on a voyage that could get there in a few decades to another star. Pretty incredible. Now, do we have a clue how to build these systems? No. But I'll tell you, the steps are being taken. As we're building these first solar sails, we're learning how to fly the sails. I work on total civilian NASA, okay? We don't do military stuff. But at Redstone Arsenal, which is in Huntsville, they're working on high energy lasers to defend troops, mortar defense, portable laser weapons. Not quite this, but on the back of a truck at 100 to 200 kilowatts, okay? These breakthroughs are going to let us take the first steps toward doing beamed energy propulsion in space, and are going to lead us down the road to being able to build the systems here to go to the stars. Laser sails are big. There are other ways you could do it. I was interviewed for a National Geographic television series last year, well, 2 years ago, and it was called Evacuate Earth. Now, why would you want to evacuate Earth? Well, they came up with a really good scenario. There was a rogue star coming our way. It's going to warp all the planets out of their orbits. We're all going to die 75 years from now. Go. What do you do about it? All right? So they asked, what are these options that we could go to the stars? I had an immediate answer. If we've only got 75 years, the Earth is going to be destroyed anyway. You build Project Orion. If you've never heard of Project Orion, man, you got to do some reading, okay? Back in the late 50s through about 1970, Freeman Dyson, who I had the privilege to meet in September, I think I've got a picture of him in here with me. Yeah, I'm a fanboy. I take pictures with people like that. Came up with this idea that you could take a ship the size of a battleship, make it airtight, put big shock absorbers under it, and start blowing up hydrogen bombs under it. Boom, boom, boom. Get it off the planet and into space. Well, it turns out they weren't crazy. I don't know if this video will play. They did some testing. Oh, thank you. Media player. Oh, good time not available. This was not going to play. So, what was calculated was a ship, think battleship sized or bigger, dropping these small tactical nukes out the back, could get 3% of light speed and get to Alpha Centauri in 140 years. I would contend if we had 75 years till the Earth was going to be destroyed, and you didn't worry about trashing the biosphere in the process, because you're doing this to save life, this is the way to go. And we could do this. Now, people ask, can you still do this? Maybe build it in space? No. It's too much mass to lift. Totally impractical. Yes?
140 years from whose perspective?
Well, that's true. 3% of light speed doesn't get you much time dilation. You don't have a whole lot of relativistic effect with that. It's there, it's real, but it's not a huge deal at 3%. You have to get up really close to the speed of light to notice special relativistic effects. Now, you can measure it, I'm sure, but it wouldn't be like the twins where you go and you come back and your twin's been dead for 150 years or something. So, good question, but it's not that big a deal with 3%. Yeah.
Are you accelerating?
It's on.
Okay. Are you accelerating halfway there and turning around and decelerating halfway, or is it just going by as fast as you can?
This would be a voyage. This numbers were just get there as fast as you can, because you don't know if Alpha Centauri is your final destination. Yeah, you want to make sure when you do your planning that you bring something to slow down, right? I mean, that would be a bad. If somebody says, "Okay, let's turn it around," and somebody says, "What?" That wasn't in the requirements document. Wait a minute. I didn't know about that. That sounds like contractors I have in my day job. So, that's a problem. You got to plan for that. You would have to slow down. But this can be done. And my message to you today is, this is not a miracle like the solar sail is going to take. We could do this. Of course, you trash the planet, but we can do this. The Holy Grail of traditional rockets is a fusion-propelled Starship. Since I made this chart, Lockheed Martin announced that they think they have a prototype fusion reactor. Have y'all heard about that? If you haven't heard about that, read about that. I don't know how real it is, but that's a pretty credible company and pretty credible people who are publishing and coming out saying that they think they can have a compact power reactor in 20 years with some breakthroughs that they've had. And I'll tell you right now, if it's real, the solar system is ours. Because once we start flying fusion starships, the solar system and sending people into ultra deep space in our neighborhood, out to that 30 astronomical unit region, becomes viable. And if it's real, this is a way we might be able to use to go to the stars. A fusion-driven starship uses the same energy process that our sun uses to produce all of its energy, to produce the power to drive the rocket, okay? And essentially, there are lots of ways to do that. Prior to the Lockheed announcement a few weeks ago, all of the fusion research was being done in facilities the size of this hotel, essentially, to get a fusion reaction to go. And they hadn't really reached and maintained what's called break-even, where you get as much or more energy out as you use to start the fusion reaction going in. And to be a viable power source, you don't want to lose power going in, you want to get more out than you put in. But if their work is real, then this is on its way to being here. There are groups that have already done concept designs of fusion starships. The British Interplanetary Society has done that back in the 70s. You can see a sense of scale here. That's a Saturn V. If you come to Huntsville, you can see one of these.
Icarus, Daedalus.
Icarus is looking at that today. Icarus, Interstellar. Oh yeah, Daedalus, that's right. That's probably what I'd rather be Daedalus than Icarus, okay? But although the Japanese were successful, what can I say? So here we go, yep. Project Daedalus. This is, you know, if you have fusion, I can see building something like this. I mean, we build big stuff all the time, right? So this is something that might be out there in the future. Now, antimatter is even better. Antimatter is not the stuff of science fiction. It's in science fiction, but it's very real. It was detected as far back as the 1930s, okay? Antimatter is nothing as weird as it sounds, all right? It is an atom, like electron, that looks just like an electron, has the same mass of an electron, but instead of a negative charge, it's got a positive charge. It's called a positron. And it has another property called in its spin state that's a little different too. But the neat thing about antimatter is that when it comes in contact with its regular matter counterpart, they annihilate and give off a burst of energy, gamma rays, all kinds of other nasty stuff. But it's the most efficient energy conversion known. It takes all of the mass and converts to energy. E equals mc squared. Nothing more efficient than that. So if you can trap antimatter and store it, you can use a controlled release of antimatter with just about anything to use as fuel and use that to drive your starship, okay? So, this is what a concept of an antimatter engine would look like. I'm going to tell you right now that there were some experiments done in Huntsville in the late 90s to try to build the world's first demonstration of an antimatter thruster. The idea was to take a magnetic trap called a pinning trap, which is basically a strong magnetic field. Quick physics tutorial. See, you're going to be rocket scientists, you're going to be nuclear physicists, you're going to have it all. Okay? Charged particles, when they're traveling and they encounter a magnetic field, just like with a bar magnet, they bend. They move at an angle. It's how your old cathode ray tube TVs used to work. Okay? So if you build a strong enough magnetic field, you can trap charged particles on the field line and it won't touch the container of what it's in. So if you pump all the air out, have the strong magnetic field and squirt antimatter in there, or regular matter, you can trap it and there's nothing for it to hit to annihilate, so you can store it. All right? So the idea was to take a truck with a power source and a magnetic bottle, go up to Fermilab, the particle accelerator near Chicago, where they routinely produce a small amount of antimatter, have them take the beamline to send the antimatter they produce into this magnetic bottle and truck it back to Huntsville. Yes, truck it back to Huntsville. And the neat thing is, now don't worry about this. They calculated that the amount of radiation that would be emitted by this little teeny tiny amount of antimatter would be about the same as a chest X-ray. So it's not like there's going to be a big bomb going off, okay? And what they're going to do is bring it back in a laboratory and do the world's first measured thrust from a small antimatter thruster. Yes, it would be mouse farts, but it would be the first time somebody's ever done this. So they get all the plans together, and somebody says, well, you know, isn't there a rule about carrying radioactive material across state lines? Don't we have approval to do that? They said, yeah, we do. So they went to, I think it was the Interstate Commerce Commission, or whoever it is that regulates trucking. And they said, you know, we want to transport antimatter across state lines. Well, you know, this is the typical government bureaucrat story, okay? But with a twist. The bureaucrat they went to said, now that's interesting. Got out a book, laid it down, and said, we have specs for that.
Sure do.
True story. The only thing I can figure is that during the 1950s, people were thinking about building antimatter bombs. That's the only thing I can figure. I have no idea why else they would already have specifications for transporting antimatter. Unfortunately, this project was canceled and that test was never performed. How much antimatter do we need? Well, think big again, folks. We need tons of it. I don't want to build the plant that makes the antimatter, that makes tons of antimatter on the Earth. If you had a ton of antimatter and you had an accident, think the killing of the dinosaurs. Okay? So you want to do this off planet. You want to have a facility in space so that if there's an industrial accident, you don't wipe out humanity. All right? So it's doable. We know how to make antimatter. We know how to store it. We don't know how to do it on a big scale. Instead of tons, the annual production that isn't even stored is on the order of nanograms. So we have a long way to go. Yes?
How far away from the Earth does the plant need to be?
As far away as you can manage to put it.
Is there a possibility you might actually in the universe?
Realistically, you know, somewhere beyond the moon. Not that far, but you know, it's a long way away. Yeah. I'm losing my voice. I'm sorry. What was the comment over here? I'm sorry, I didn't hear you.
Was there a possibility we might actually end the universe?
No. Nature, you know, I'm telling you to think big with this stuff. That's still small potatoes compared to what the universe is doing out
The
there.
asteroid belt used to be a planet. They made antimatter.
That's it. That's another story. You're good. Thank you. I'll write that down. So where I want to leave you with this is, you know, we live in a society today where I think we have diminished expectations. We don't think big anymore. You know, we seem to be really, I'm serious, we don't. You know, at one time we thought big. We thought about going to the moon and we did it in 10 years. We thought, wait a minute, we got to beat those Nazis so they don't kill us in the war. We have to invent something called nuclear power and make it into a weapon and use it. We did it. All right? We had to think big about a Navy that protects every, you know, free commerce around the world. We do it. The highway system. Have you ever imagined how, when my dad was a boy, I mean, you know, driving across country was like driving, you know, a 2-lane road, but half of it was gravel. You know, and now we have this wonderful interstate highway system, which is an incredible achievement. We don't think big. Well, I'm trying to challenge people to think big. I gave a TEDx talk on this. It was called Think Big. We can't do this today. Your kids probably won't do this. But unless we start taking the steps now and laying the groundwork and people think it's possible, we'll never do it. So I'm just kind of trying to motivate you and let you know that there are still people thinking big out there. Yeah, question.
So when I think solar cells, I think mylar blanket. Is that correct? Or
You can use mylar, where there's another polyimide called CP1, which is an aluminum-coated plastic, essentially. And I'll have a piece of it to hand around at the talk tomorrow. So you need to come to my noon talk on solar cells, and I'll have a piece of solar cell material, like we're actually going to fly, that I can hand around for you to feel. So no, you won't float away with it. Sorry. Yeah. So let me just get to this, and I'll take any more questions. The other message I want to tell you is that the laws of nature have not told us we can't go to the stars. The laws of nature have said if you want to go to the stars, you got to work for it. It's going to be hard. And so the question I have is, and it's for you to think about, is are we up to that? You know, are we as a species going to essentially remain trapped here forever, or one day are we going to take that voyage? And I'm hoping that some of my descendants will do it. And I'll tell you, as a personal side note, we had one of those interminable management training classes that I had to do at work. And they ask people, you know, what motivates you, or how do you want to be remembered? And you would think this would be common at a place like NASA. And remember, I'm speaking as a private citizen, recounting a personal experience, not speaking for the agency. And my way I want to be remembered is when the first colony around another star is written, and they're writing the history of that, that something I worked on is a footnote in that history book. That's what I want to be remembered for. And of all the people that were in that class, I was the only one that had anything space related in what they said they wanted to be remembered for. And, you know, I love my kids and all this, but I want my kids to look at that and see that was my great-grandfather who did that, you know, or my great-great-grandfather who did that. So anyway, that's what motivates me. Yes, sir.
Well, I got two quick comments.
Yeah.
Quick comment.
Sure.
When I was in college, deep in the last century, we had somebody from your agency, NASA, come to the dormitory I lived in. And they were promoting the SETI project, basically send up an antenna and listen for alien radio signals. And I looked at one, this is little mid-70s, and I said to the gentleman,
Groovy.
look, I said, gentlemen, you know, we grew up with Lost in Space and Star Wars and Star Trek and all this other stuff. We don't want a radio antenna. We want a TIE fighter. The heck with this crap. And so 4 of my college friends gave me TIE fighters at Christmas. So my question to you is, on a more serious note, so great, we're going to have this sail the size of Texas. Now, how far away from all of the space junk do we have to get so that the sail doesn't get perforated?
Well, I've asked that question a lot, and you're going to assemble this big sail not on the Earth and launch it. You're going to assemble it in space. And space junk's really restricted to Earth orbit. If you get out beyond Earth orbit, it's mostly just empty space except for a few micrometeors. And we've done hypervelocity impact tests, which are kind of fun, of the material. And it's so thin that this stuff moves so fast it goes through without depositing much energy, and it just makes a little minor pinprick. And the sails actually have ripstop in them, so if you get a tear, it's not going to go very far. Now, if you took a block of aluminum and hit it with that same micrometeorite, it would explode because it's thick enough that the energy is all deposited in there, and all that heat's got to go somewhere from that kinetic energy, and it causes it to explode. But the sails are so thin that it really, you just punch a little hole in it, and that's it. So it really is very survivable.
And the perforation doesn't deteriorate the sail characteristics?
No, because of the ripstop. Every half a meter, there's a Kevlar cord going through, which is ripstop. So if you do get a tear or a big hole, it's not going to propagate. Yeah. Any other questions?
I have one here.
Yes.
Okay. My question is, you were talking about all these different places having all these different projects. How much cooperation is there between all the scientists?
There are regular conferences where we share results, and I'm a co-investigator on the European solar sail. And so I see all their design data, and I'm a part of that. So it's very collegial. Although there are some working on it that are very competitive. The Japanese were very competitive. They basically told us everything about their sail after they flew it, because they wanted to be the first to fly an interplanetary solar sail. And I don't blame them. It's way cool. They did a great thing. I'm sorry? I think competition can be a good thing. I really do. I think it gave us a kick in the pants. And I think it's what helped spur the European and the U.S. solar sail efforts, was to do that. Now, I don't know. I've heard that China's working on one, but we won't know until they fly it, in all likelihood, because they're very secretive about what they do. So there's a mixture of competition and cooperation. It's a mix. And that's in all areas of space science, really. It's a mix. All right, well, very good. I appreciate you all coming out tonight. If you're interested, I have copies of my books for sale back there, both my nonfiction as well as the science fiction. And if you want to buy some, I'll be glad to hang around. Kind of helps pay for me being up here this weekend. So if you have any other questions, I'll be hanging around tonight, and I'll see you tomorrow at the Solar Sale Talk. Thank you very much.